Now, with the introduction of these coordinate systems, we come across a few vectors, they are the unit vectors along all the coordinates what we have in each coordinate system. By considering these unit vectors, we need to develop a vector, or we need to take a vector in three-dimensional space. So, for that vector, vector itself is not sufficient, we need to add some other vector if it is required, or we need to subtract some other vector if it is required, or there may be some multiplication between two vectors. So, here the vector analysis is essential for understanding the electromagnetic theory. Now, what we do is we will consider some general vectors and we will take different operations between all those vectors. So, before that, what is vector? A vector, it's already we know, a vector is nothing but a quantity which has both magnitude and direction. So, if we are saying something is in that particular direction, then it is said to be a vector. That here in our electromagnetic theory, all the quantities, almost all the quantities what we consider are vectors. In the circuit theory, basic circuit theory, what we have are voltage and current. They are pure scalar quantities, but those voltage and current are not suitable to examine our electromagnetic theory, or the concepts, to understand the concepts in our electromagnetic theory. To understand the concepts in electromagnetic theory, we require a vector called as electric field, another vector called as magnetic field, or which are related to some other things like electric field intensity, electric flux density, magnetic flux density. Like that we have different components, all they are vectors. So, what we need to do is we have to go for the analysis of vectors. A vector has a particular quantity which has a direction as well as magnitude. So, this length will represent the magnitude of that particular vector, and the arrow mark what we have drawn will represent the direction of that particular vector. So, you can take any direction. So, for as an example, you can I took in this direction, you can take a vector in this particular direction according to the requirement or problem that what we have. So, here clearly if you observe this vector has a head and tail. So, this tip is called as head and this tip is called as tail. Now, we need to understand this vector in different coordinate systems. To draw the vector in our all coordinate systems, so we have coordinates, already we discussed that, that's x, y, z, rho, phi, z and r, theta, phi. Now, what we do is we will take our base, our rectangular coordinate system as base, and we will discuss entire vector concepts with respect to the rectangular coordinate system, and if required we will develop the same concepts for remaining all coordinate systems. So, let us take an example. A bar is a vector which is given in rectangular coordinate system. Already we said, and I discussed that this can be written as ax plus ay plus az. That the vector notation of A can be written as the components ax, ay, az in the direction of x, y, z. In the same way, we can represent another vector b bar like this. Let us take this is b bar, which is equals to bx ax plus by ay plus bz az. So, here clearly the point A is represented with the coordinates x, y, z, ax, ay, az, and B is represented with the coordinates by, bx, by, bz. They are called as the components of the vector also. That the vector components of A are ax, ay, az, and the components of vector B are bx, by, bz. So, if you want to denote the two vectors in the point form, simply A bar can be written as ax, ay, az, and this b bar can be written as bx, by, bz. And if you are drawing this one in a two-dimensional plane like this board, it is very easy to observe the direction. So, simply it is in this direction, the B is in this direction, A is in this direction, some other vector may be in this direction, but we are treating every quantity in our electromagnetics in three-dimensional space. So, the two-dimensional plane what we are considering is not sufficient to get the direction of a vector which is coming out of the board or which is going into the board. For that we need to take a small notation. So, whenever a vector is coming out of the board, what happens? Whenever a vector is going into the board, how to represent it? For that we have a small notation. For that, consider a vector like this. This is the head and this is tail. Now let us take from this plane of board, if a vector is coming out, from the plane of board. So initially what we visualize is the head. Since the head is visualized, or since the head is seen from the plane of board, just a tip of this head can be viewed. So if you want to represent any vector which is coming out from any plane, a plane of board, then we need to represent that one with a tip surrounded by a circle. That initially this tip is visible, that the head is visible. So it is coming out, that what we can say. If the same vector is going into the plane of board, then we can observe the tail. Since we can observe the tail, the shape of this tail can be like this, that is like an into, that is going into the board, right. So clearly if a vector is coming out of the board, then it will be represented with a tip, and if it is coming into there, so going into the board, then it is represented with an into mark. Just you remember like this, into stands for into the board, and the remaining one point stands for coming out of the board, right. So now we will have different operations on vectors. So what are different operations on vectors? Same as your arithmetic operations, we have different operations on vectors like addition, subtraction, multiplication, but there will be no division. So what we do is we will discuss one by one. So how the vectors will be added, how the vectors will be subtracted, and how the multiplication of the vectors is defined. So we will start with addition of the vectors. So if the vector is given as its original form, that the vector is represented like a simple line in this space, another vector is represented as another line in this space, how to add them? Or if a vector is given as a point in this space, another vector is given as a point in this space, how to add them? We will discuss these two techniques. The first one, if the vector is given as a line in space, that is, let us take this is a bar, that the vector is in this particular direction, and another vector b bar is given like this. These two are the vectors. What we have, the magnitude of this vector is this much, and the magnitude of the second vector b bar is this much, and these two are the directions, they are in two different directions. To add these vectors, just what we have is a pictorial representation of the vectors. We don't have any points here. So what we have to do is, we have to take the pictorial representation of the vectors and we need to combine them for addition. Right, for that we have a simple rule called as head to tail rule. That another rule is there, that's the parallelogram rule, but this head to tail rule is a very much interesting and a very simple rule to add two vectors. That head to tail, or some may call this one as head and tail, but head to tail, head and tail, so both are same. That the rule is like this. What we need to do is, we need to join the head of one vector with the tail of another vector. Don't bother about the head and tail of the vectors, just head of one vector will be joined to the tail of another vector, whatever it may be, that may be either a bar or b bar, right. Now you may get a doubt, sir, if we are joining them, that we are relocating this particular vector a bar or relocating this particular vector b bar. No doubt about it, it's even though you are relocating the vector without changing its direction and magnitude, the vector was unaltered. So if you move this a bar from this location to another location without changing its direction and magnitude, the vector remains same. If you are moving this b bar from this location to another location, the vector remains same. So what we have to do is, just we need to join the head of one vector to the tail of one vector, another vector. So what I do is, here I will take the head of b bar, I will take the tail of a bar. So I will try to join the tail of a bar with the head of b bar. For that, so without changing any direction and magnitude, I will shift this vector to this location. So what I have is a vector like this. This is same as your a bar. So these two must be parallel. And so while we are drawing, these two must be parallel and the magnitude also must be same. Now the second step what we have to do is just join the tail of the vector, first vector, to the head of our second vector. So this is nothing but a bar plus b bar, that we are moving from this point to this point. So the result can be obtained in an easiest way by considering head to tail rule. The head of one vector will be joined with tail of another vector. That we may get doubt that why we have to move this a bar, and so we can move this b bar. So why can't we move this b bar? We can move this b bar also, no doubt about it. That what we need to do is bring this b bar to here and that the head of this b bar to here. Then what we will get like this. This is b bar. What I did is just I moved this b bar from this location to this location, that I have not changed any direction or magnitude. Once again join the tail to head, what you will get is a bar plus b bar. Here in this case this may be b bar plus a bar. Initially what we have is b bar, therefore this can be written as b bar plus a bar. Here also it is b bar plus a bar and a bar plus b bar. So both are same. So clearly what we need to do is we need to take one vector and just shift that vector to the appropriate location, that is the head of another vector, and consider the resultant from one point to head to tail, that's a tail to head. Then that is the resultant of our a bar and b bar. Now if the point is given to us, then now consider a point representation of the vectors. If the point is given like this, that is a vector is given as 3, 4, 5. So in general, instead of taking the numbers, what we do is we will take the components. So let us take a bar as ax, ay, az. So these are the components of vector a, and the components of vector b, bx, by, bz. Then the vector addition of these two is a very simple one, that the point to point addition of the components, that the x component will be added together, so the y component will be added and z component will be added. So if you want to write this a bar plus b bar, then you can write this one as ax plus bx, that is the x component, ay plus by, that is the y component, and az plus bz, that is the z component. So the corresponding components of x, y and z will be added, so that what we get is the addition of these two vectors. So a simple addition, that's when it is a pictorial representation or graphical representation, and when it is a point form. Now in the same way the subtraction also will be taken place. If you are considering the subtraction of two vectors, once again we will discuss about the subtraction in both pictorial representation as well as point representation. So if you have two vectors same as our previous one, let us consider this is a bar and somewhere we have another vector b bar. If you want to calculate a bar minus b bar, that the b bar will be subtracted from the vector a bar, then what will be the resultant? As we know, if you want to get the negative of this vector, just we need to alter the direction of that particular vector without changing its magnitude. So what we have to do is, to get this b bar, just alter this one, that is change its direction exactly opposite to it, then what we will get is b bar. Now once again the principle is same, that a bar will be added with minus b bar, that what we get is a bar plus minus b bar is a bar minus b bar. So for that what we have to do is, you have to take this vector minus b bar and move this particular vector to the appropriate location of a bar. That is nothing but head to tail rule again. Here what we have is head of a bar, and here this is the tail of b bar. So what I am doing is, I am connecting this tail of b bar with the head of a bar. So without changing its magnitude and direction, as it is I will shift to this location, then it becomes minus b bar. So clearly the b bar was shifted from its location to this location without changing its magnitude. Now move from the tail to head, that is a bar minus b bar. So the resultant will be in this direction, this is a bar minus b bar. So the subtraction is not that much difficult. If we know how to add two vectors, obviously we know how to subtract two vectors also. That the subtraction will take place with the help of alteration of one vector, that the direction will be changed, right. So if we have points, that is a bar, so if you generalize this one as ax, ay, az, b bar, bx, by, bz. The subtraction is similar to the addition, that the corresponding points will be subtracted, that a bar minus b bar is equals to ax minus bx, ay minus by, az minus bz. So the pictorial representation as well as the point representation for our vectors as a bar and b bar is generalized like this. So if you have values for this one, numerical values for ax, ay, az, then we may have some components or we may not have some components when they are added or subtracted. So this was represented for a purely rectangular coordinate system. The same is applicable for the remaining two coordinate systems also. So the corresponding components of rho phi z will be added in our cylindrical coordinate system, and the corresponding components of r theta phi will be added in our spherical coordinate system if the point form is given, or if the vector form is given, arrow and some other direction vector, these two will be added. So the basic principle remains same, but the components what we are considering may change. So this vector and subtraction will be somewhat useful in our electromagnetic theory problems, that somewhere so to analyze our electromagnetics in a cylindrical coordinate system or spherical coordinate system, or at some point in free space, we must add two vectors so which are coming from two directions, the two electric fields. We may add two electric fields, or we may add electric field and some other vector. So for that, the addition and subtraction are useful. Next what we have is multiplication of the vectors. That multiplication we will discuss in our next session.